Welcome to our presentation. Our group will be presenting on unmodeled dynamics by Andrew, Alec, Jacob, Kinsey, and Sydney. Engineering is all about making simplifying assumptions. In real life, there could be an infinite number of factors contributing towards the physical nature of a system, so it is impossible to account for everything. Therefore, engineers must decide on where to make their truncations when generating mathematical models. Those state variables that are kept within consideration are what engineers will assume control over when designing reactional dynamic systems. The variables that go unconsidered are left uncontrolled and are what make up the branch of unmodeled dynamics. Generally, in modeling spacecraft attitude dynamics and controls, spacecraft may be assumed as rigid bodies. This is typically because the most critical components are placed within the spacecraft hub, which is designed to be very stiff. The orientation of a spacecraft's appendages are not as critical, yet they may experience oscillatory and damping motion or vibrations. Additionally, factors that go unconsidered usually involve a very convoluted analysis that may not have an exact solution. The sloshing of liquid propellant is a good example of this. Engineers must make the decision on whether or not their truncated models are accurate enough representations of a system's dynamics. In those cases where they are not, some of these common unmodeled components may be brought under consideration.
Flexibility in a spacecraft and propellant sloshing are two disturbances that often go unmodeled. Attitude maneuvering introduces vibration modes into the flexible appendages and the propellant, deteriorating pointing performance. Maneuvering is further complicated by instantaneous change in center of mass from movement of the flexible elements. Deformation in very flexible spacecraft will strongly influence the magnitude and distribution of external and internal forces, causing deflections and accelerations to become superimposed on average measurements by sensors. This can cause the control system to give erroneous command signals that could destabilize the spacecraft. Generally, a pointing error budget is established for the different operational modes of a mission with unmodeled dynamics as a time-random pointing error source. Each error source is statistically analyzed to find a max expected value. In certain cases, slosh and flexibility analysis must be performed to better estimate the disturbance. The level of detail required depends on amount of propellant, attitude determination accuracy, and the mode. Slosh effects are more prevalent during thruster-based modes or orbital maneuvers. If slosh analysis is required, it can be performed using computational fluid dynamics software, but this requires specialized knowledge. It's extremely difficult to find an exact solution for fluid oscillations in a moving tank, which is why slosh is neglected if possible. A simpler but lower accuracy alternative is using equivalent mechanical slosh modeling. These models consist of a mass spring, pendulum, or complex motion system. The larger mass in the figure is the mass of the propellant that moves with the tank, while the smaller mass is the first mode of motion of the free surface. The accuracy of these models depends on the knowledge of model parameters such as tank shape and fill fraction. The pendulum is the primary model used in missile or rocket applications because it includes a damping parameter and accounts for the low-G environment. For flexibility analysis, the spacecraft is divided into flexible appendages and a rigid hub that usually holds ADCS hardware with critical orientation needs. The equations of motion are a function of the mass and stiffness matrices, applied torque, and the elastic coordinates. The B vector in this equation couples the attitude motion with the elastic deformation. If the hub is fixed, we obtain what are called the constrained flexible spacecraft equations. For more realistic structures, a damping matrix is added to the equations. Further analysis leads to the fundamental natural frequency and mode of vibration. Flexibility can significantly change the open-loop gain frequency response of the controller near these modes and lead to destabilization. Keeping the open-loop bandwidth below this frequency is called gain stabilization and allows the controller to be designed as if the spacecraft were rigid.
The action of a system can be described by the linear combination of all the modes. These modes are sinusoidal functions of varying amplitudes and frequencies, which when all are superpositioned, it creates an accurate model of the behavior of the system. Unfortunately, real-world dynamic systems take an incredibly large number of modes to model. The general solution to this is to truncate the number of modes and assume there will be an error within the model. As we now know, these truncated terms will be known as unmodeled dynamics. In these real-world scenarios, our systems that depend upon dynamic systems do have a way to accurately respond to the modeled and unmodeled dynamics. It is called a controller. A controller takes real-world data in from the system to know how to react. This means that all of the modeled dynamics and noise due to the unmodeled dynamics is included in the controller's evaluation. By far the most common controller used is the PID controller, and the effectiveness of your PID controller is heavily dependent on the control loop rate that it is using. Too quick of a rate, and it will take into account all of the noise in the system, which is generally a problem, and too slow of a rate will make it unable to recognize smaller trends in the data. The general rule of what the control rate should be is 5 to 10 times the process time constant. This will typically give data with minimal noise, but precise enough to demonstrate the trends within it. The process time constant is the time it takes for your controller to reach 63.2% of its total change in what it is measuring. If this sounds complex, that's because it is. This process generally is completed manually with an analysis of step test data. Combining these two ideas, noise in a real-world system would be the unmodeled dynamics, which are things that do not match up to our simplistic model. The faster our control loop rate is, the more accurately we will measure the noise of the system and give us an in-depth response to the minuscule behaviors. On the other hand, having a standard control rate allows the controller to base its behavior on the overall trend of the system, which is very similar in idea to truncating terms of the dynamic system. In most cases, it is not necessary to base your controller on the finest level of detail, but it is important to understand the overall behavior of the system.
When it comes to control strategies and mitigation in unmodeled dynamics, there's really two cases that we look at, which are spacecraft flexibility and propellant sloshing. Now, for spacecraft flexibility, this one is the most easy to deal with. There's really three ways that we kind of consider when looking at how to deal with this unmodeled dynamics problem. So first, you can keep the open loop bandwidth below the fundamental vibration frequency, which this is called gain stabilization. This just means that we want to prevent or make sure the spacecraft doesn't approach the natural vibration frequency so that it becomes destabilized. This is a simple solution and allows for the rigid body assumption that we usually use. The problem with this is that it can limit performance, especially if the fundamental frequency of the spacecraft is low. So it can limit the performance of the spacecraft. The second strategy is you can add compensators to the controller, which this is called phase stabilization. This allows us to not limit ourselves and not limit performance. However, this means that we must know more information about the spacecraft, and we must know the corresponding vibration modes for the flexible spacecraft. And thirdly, we can use state space representation and model the flexibility of the spacecraft in the time domain. This can be very effective, but it means that we have to continually monitor and model the spacecraft's movement. Now, when it comes to fuel sloshing, there's a lot less that can be done about this problem because it is very complicated and much more complicated than the flexibility of the spacecraft. However, through research, it's been found that the sloshing problem is most significant during thrusting, as the fuel has a force put on it. The most effective way to limit this issue is by putting baffles in the fuel tank, which prevents the movement of the fuel as much as possible.
Air-breathing hypersonic vehicles are very difficult to model and control due to the strong interaction between airframe and engine dynamics. The vehicle's slenderness and lightweight structure cause vibration, and since some operational parameters depend on the vehicle's state, this leads to uncertainties in system dynamics. A study in the design of L1 controllers in the presence of unmodeled dynamics allowed for pitch angle, flight path angle, and velocity to all follow their given respective reference signals. In the simulation results shown, the pitch angle tracks the desired pitch angle command very accurately.
That concludes our presentation. Thank you for watching.